Hey, welcome back. This episode, I want us to take a look at modeling atoms, and particularly modeling, we're going to actually how to look at something that is a partial model and figure out which isotope is it, and then some details about it, how to properly identify the components, how to properly write some notation, and then problem solve from there with it. So let's just go ahead and jump in at looking at determining the isotope and some different notation forms. Let's take a look. We have an isotope, some isotope. We don't know what this isotope is. We have to identify it. That's what the problem is asking us, right? So we need to identify the number of protons, neutrons, electrons, valence electrons, valence. It's pronounced both ways. Write the isotope notation and the Lewis structure for this isotope once we identify it. So what we have here is just some dots, and those dots, we know the blue ones are protons, the gray ones are neutrons. So with this said, we ask ourselves, how in the world can we use this to actually figure out what in the world this thing is? Well, if we look closely, we just sort of problem solve this just a little bit at a time here. We've got the protons are in blue, so we can count this and we can see that there's 1, 2. Pardon me for a second, more detail. We can see there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 protons. So we have 13 of these things here. Neutrons, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Let me try this again, make sure. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. We have 14 neutrons. There are no electrons on this, but we already know that if we have a stable atom, that the number of protons that we have and the number of electrons, they will be the same. They will be the same. And because an atom, by definition, has a neutral charge. So if you have 13 positive parts, you have 13 negative parts, right? That's, by definition, that's what an atom is a neutral form of the element. Whereas something like an ion will be a charged form of the element. And so there will not be an equal number of protons and neutrons. Those things shift, and we look at that in other videos, right? So we've got 13 protons. So obviously, what do we need? We need a periodic table. So I happen to have one here. We go to the periodic table, and it's the same one that we use in class. So atomic number 13, we can see here. We've got atomic number 13. Let me zoom that in for you, and you can see atomic number 13. That's aluminum. All right. So right there, where we have we know aluminum, we know two things from this. We know that that top number is the number of protons, the atomic number, and the bottom number represents our average atomic mass because of the various isotopes, right? So 26.982, it's going to round up to 27. So we know we have a mass of 27, and we have atomic number of 13, so that's the number of protons. So let's go back to what we're working on. We know that the total number of protons identifies the element itself. So we've got aluminum, all right, a capital A, lowercase l. And we saw that the mass was 26.982. That rounds up to 27. So remember, that goes on the top left as a superscript. And then below that is always the atomic number, 13. All right, so 27 minus 13, 14. So that's our number of neutrons. So obviously we've counted correctly. So check, write the isotope notation. Check that part is done. Isotope notation is done. Now what we have to do is we need a Lewis structure for this. And I'm going to save the Lewis structure for the last part. If you already know how to do the Lewis structure, that's really easy. You can actually, once you know how to do them, what they are, looking at the periodic table is you can figure out what the Lewis structure is just by looking at that. So by the end of this lesson, if you aren't already familiar with that, you will be. So we've got aluminum. We need to complete a model of it. And so what this is essentially asking is a Bohr model. So where it's saying complete a model of it, right here we're saying basically a Bohr model, right? And this is, let's just make a Bohr model. And we know a Bohr model, two-dimensional, it doesn't represent necessarily the best form of the atom, but it is commonly used that we can be in our first initial studies of chemistry to understand how things are placed. We got a nucleus, we got the first orbital, we got the second orbital, we got the third orbital, and so on and so on and so on. It just keeps going out and out and out. All right. So aluminum. So let me zoom back out of this for us. So aluminum, we can see is in period 3, right? And period 3 tells us that we have 3 orbitals. So there are 3 orbitals around the nucleus of this atom, all right? So let's go back and let's do that. Let's get our little geometric tool here. Let's get 3 orbitals around this. First though, what I want to do, let me just take this and I want to resize this. I'm just gonna just bring that down just a little bit, and then let's put that over here. Okay, I'm just already anticipating some room that I might need. All right, geometric tool, so I can get some nice shapes here. So we've got the first orbital, and remember our first orbital. Well, we said we had 3 orbitals, so let's just go ahead and get the 3 orbitals on there. So there's 1. There's 2. There's 3. That's good enough. Close enough. We could have put that second orbital a little further away, but this will be fine. This will be fine. It'll be okay. All right. And let me change color. Electrons, red. So I'm going to go ahead and change all of this to red so everything is color coded perfectly for us. Remember we said we needed 13. All right, we're going to need 13 electrons altogether, right? So we've got 13 electrons we need to start out with. All right, so well in the first period, period 1, where we're going all the way across, we see that there's space for 2 electrons. So conceptually, we can think of each of the squares, each of the spaces on the periodic table as like a place in some three-dimensional sort of region around the nucleus where an electron could be. All right, let's put that in air quotations, which looks a little cheesy, but it's true. It's like sometimes it could be here, sometimes it could be there, which is a much deeper lesson. But for right now, wherever there is one space on the periodic table, we can think about that as corresponding to a place in the space of an atom where an electron fits. So in period 1, we can see that there's 1, 2 spaces. So let's go back, and I'm going to put 1, 2 electrons. So now subtract 2 electrons. We still need 11 more electrons. Okay. So now let's go back. We got to the end of the first period, so we need to go back, go down to the second period, and we can see 1, 2, 3, 4, 5, 6, 7, 8 gets us all the way across the second period, all the way over there to neon. So now that second period has 8 electrons and it's full. So we go back and we put 1, 2, 3, 4, 5, 6, 7, 8. And I guess I could have done a little better job spreading these out, but conceptually that's all we need to worry about right now. They are as evenly spaced out as possible, depending on, and they're not always evenly spaced out, but you want to try to typically space them out as evenly as possible. All right. So we just added another 8 electrons. So according to this, there's only 3 electrons left that we need. Well, let's see if that makes sense. So we filled the first orbital, the second orbital. So we go back down, drop down to the third. And we can see there's space 1, 2, 3. That gets us to aluminum, which makes sense because we have 3 electrons left. So we go back and we're going to put an electron here. I'll put an electron here, and I'll put an electron there. So we just added 3 more electrons. We've accounted for all of our electrons. We got them all. We're good. So there's our Bohr model. Check this thing. This thing is done, and it's properly built. You always build from the inside out. All right. Now let me get out of the red here. I'm going to go back to like a classic dark blue that I really like. So identify the number of protons. Well, we've done that. Check 13. Identify the number of neutrons. Check 14. The number of electrons. We already said we needed 13 electrons because we needed this to be a neutral atom. Check. We've done that as well. Valence electrons in the isotope. It says each isotope. Forget it says each. Forget it says each. At one time, the way I had this problem written, there was going to be multiple of these things here. But what I've decided to do is split this lesson into multiple lessons. So I'll leave this one like this, and I'll do another one later. All right. So now we need a Lewis structure. So a Lewis structure, by definition, a Lewis structure shows us the number of valence electrons. All right. Lewis structures tell us how many valence electrons the atom possesses at that time. So valence electrons, again, are the electrons on the outermost part. So a lot of times, if you think of like on a wall where curtains are, sometimes there's that little part that goes on the outside, like on the top part, and it goes on the outside. It's called a valence. It's pronounced. Oh, that's a valence that you put on there. That's an example, and it's because it goes on the outside part. So valence, valence, it's pronounced both ways. Those electrons are the ones on the outermost part. Well, we can see here that we have, on the outermost part, that would be the third orbital. So there's one here, there's one here, and there's one here. So we have 3 valence electrons. So the way you write a Lewis structure, first and foremost, you write the element symbol, and then you literally put how many valence electrons do you have. So we see that there's 3. So we put 1, 2, 3. And we're done. There's Lewis. Sometimes the Lewis structure is called a Lewis dot diagram. And the reason why it typically, sometimes more often, might be called a Lewis dot diagram is for the reason that you see here. You have the element symbol, and then you literally just put the number of valence electrons that are orbiting the atom. And the maximum number that we're going to be working with will be that magic number 8. All right, you're going to be working with the magic number 8. 8 valence electrons, no more. And the reason for that is 8 gets, when there's 8 electrons on the outermost orbital of an atom, it's most stable. So if we go back to the periodic table, then and let's just sort of zoom in here a little bit. Remember our noble gases, the oxidation state is 0, right? And the reason why it's 0 is because 0 electrons are needed to fill that orbital. So where helium is, all right, we can zoom out a little bit more again. Hopefully you're following along, but where helium is, you can see that there's, in the first orbital, there's only room for 2 electrons. One in the space where we see hydrogen, and another one right there where helium is. So there's only 2 in the first orbital, all right? In the second orbital, where lithium is all the way to neon, there's a total of 8 spaces. There's your 8 electrons. It is stable. So if we have a neon atom, it doesn't need any more electrons. It already has all 8, all right? And then drop down for the third period from sodium all the way to argon, same is true. So this gets us into talking about oxidation states, right? So if you look at those numbers that are on the top of the periodic table, right? All these numbers that are on the top. So we see that 0 right there for the noble gases because they don't need any. Well, fluorine, where we see fluorine at, by the time we get to fluorine and count all the way across the fluorine, we have 7 electrons in the second orbital. Well, fluorine, if it were to take away 1 electron from somewhere else, that means it takes it away from another atom, it would now have the 7 it already had plus that 1 more. That would get it to neon. The outer orbital would be full, and the outermost part is more stable now, but it would gain a charge. It gains one more electron, so it would be charged by a -1. Where you see a positive value, it's the opposite. What happens is those atoms are adding those electrons elsewhere. So let's zoom out and let's come over here. Let's just start with some of these smaller ones. So let's just take beryllium. Beryllium, you see it's a +2. All right. Well, beryllium is in the second period, and you can see that we have an electron in the first and the second space, in the first and second place in the second period. Well, if those two were added elsewhere, it would be, then the second orbital would be empty, and just the first orbital would be full. All right. If that's confusing to you, let's just use our example of aluminum. If we zoom out and find aluminum, remember we had to add 1, 2, 3 electrons into the third period. If all of a sudden aluminum, which we see on the periodic table, that aluminum, if you go up, aluminum has an oxidation charge of +3. We typically write it 3+. So as an ion, aluminum is written like this. So that means it will take 3 of its electrons will be added elsewhere. Well, if it does that, then what that means is this electron goes away, this electron goes away because it's somewhere else, and this electron goes away. So effectively, what happens is that third orbital around aluminum has no electrons, and so that region of space, we just don't even think about it. Now you can see that by aluminum adding 3 elsewhere, all right, that now the outer orbital for that aluminum ion would 1, 2, 3, 4, 5, 6, 7, 8. It's full, it's stable. So there'll be another lesson where I'll show you how we draw that. This is what happens. This is what happens back and forth with chemical reactions. Electrons are just moving back and forth between atoms, shifting, moving back and forth between different orbital spaces, and depending on the atom, depending on its properties, depends on if it's negative or positive and how many electrons are moving. All right? I think that's a good place to stop. All right? That was good. Check out the other lessons for some more examples. Hope this helped. That was pretty straightforward. The atomic number, the number of protons, will always define the atom. That is first and foremost. That trend never goes away. So if you can figure out how many protons are there, from there you can work your way up and use the rest of the information to fill in the rest. It's very important to understand that periods, that trend right there, a period lets you know how many orbitals you're working with, and that your groups, there's also characteristics with the groups, particularly your oxidation state. So that lets us know something about the charge. For now, you can also use the period to figure out how many valence electrons are there. We saw that in the video. And Lewis structures, it's a very simple shorthand notation. And the reason for that is we use that in other notation, other things that we're going to be using in class where we need to write out processes and stuff like that. So it's important that we be able to draw the Lewis structure because it is an abbreviated way of showing that model. But it just takes what we need, which is the valence electrons, because that's where the reactions are happening. So when we do all this stuff with chemical reactions, it's the valence electrons that are interacting back and forth, and that's the important part. And so that's really the main reason, for starters, why we need the Lewis structure. So you're going to want to be able to get to the point where you can write a Lewis structure, you can figure out the number of neutrons, number of protons, number of electrons, isotope notation, all of that just by looking at the periodic table. There's a wonderful amount of knowledge there. The more you use it, the easier it gets. You don't have to memorize any of this stuff. Just use it. The more you use it, it's going to stick. You're going to get it. Practice makes perfect. I'm going to have more examples of this type of stuff, and you should just pick one randomly and give it a shot and see what happens. But I'll have plenty of examples for you. As always, it's good talking with you. I'm glad you could join me. Stay curious, and I will see you in another lesson soon. Bye.